All right, for chapter 20, we're just going to do problems 2, 3, 4, and 7, and you'll see that in the homework. All right, so let's get started. Let's take a look at the first question. So number 2 says the radius luminosity temperature relationship. Okay, so we should be familiar with that by now. I'll go over it again. Use that to calculate the radius of a red supergiant with a temperature of 3,000 Kelvin, which is half the value of the sun, and a luminosity 10,000 times that of the sun. And the second part of this question, how many planets in our solar system would this star engulf? Okay, so basically you just look and you figure out what the radius of the planet of the red supergiant is, and then we'll see how far out it goes. All right, so let's get back to this this particular thing. Let's see. All right, so here's the luminosity, radius, and temperature relationship. Okay, so we're going to use that to solve for problem 2. All right, so generally, when you use this, you use it in the following sense here. Actually, let's make get a little bit more room here. Okay, so we're just going to. So again, remember, we're just doing problem number 2, and so the way that we do this is we compare we look at the luminosity relationship in comparison with the sun. All right, so the luminosity of the red giant, right? So because we're talking about a red giant, divided by the luminosity of the sun, right? Or our sun, of course, because that's the star we know the best, is equal to. So it's going to be the radius of the red giant divided by the radius of the sun, and of course that's squared. Remember, what we're really looking for is the radius of the red giant. So we're going to solve this for that, anyhow, the temperature of the red giant, which they gave us, divided by the temperature of the sun. By the way, this time what we're going to use, since they told us in the problem that the value of the temperature of the red giant was half that of the sun, we're going to use the temperature of the sun as 6,000 Kelvin. All right, so this is to the 4th power. All right, so we just have to rearrange this equation and solve for what I circled right here, the radius of the red giant. All right, so and we'll keep everything squared for right now. All right, so this is what it's going to look like. Notice the temperature of the sun. We'll go over to the other side, and that'll go in the numerator, and then the temperature of the red giant will go in the denominator, but it's still going to be to the 4th power. So here's what we get: the radius of the red giant divided by the radius of our sun, and of course that's squared, but I'm going to show you. We're going to take the square root of the other side. So what is that equal to? That's equal to the luminosity of the red giant, and divided by the luminosity of our sun. So it's compared to it's the luminosity compared to the luminosity of our sun. All right, and they give us that value, right? Remember, since this is squared, we're going to we have to take the square root of both sides. So this is going to be the square root of that, and then of course we're going to take the square root of. So this is going to be T, the temperature of the sun, divided by the temperature of the red giant. Remember that it changes places because this is in the denominator, and that's got to go over to the other side of the equation. All right, and then all right. So anyhow, when we take the square root of that, then the square root of something to the 4th power is just squared, right? So this is the equation that we're looking for. All right, so I'm going to rewrite that, and this is what it looks like, and then we'll put the numbers in. All right, so the radius of the red giant is going to equal, remember, it's going to be the square root of the square root of the luminosity of the red giant divided by the luminosity of our sun. So remember, that's that value. The luminosity of our sun is 1, and we always get the luminosity of other stars compared to the sun, right? All right, and then the temperature of the sun, remember, we're going to use 6,000 for that, divided by the temperature of the red giant, and that is to the 4th power, squared, right? Remember, because we have to take the square root. All right. So that's it. Now we just have to put the numbers in, all right? So this is actually fairly easy. It's just the square root of, and they gave us that the red giant had a luminosity 10,000 times that of the sun. So it's going to be 10,000, all right, divided by 1. You don't really have to put the divided by 1, times, remember, it's the temperature of the sun. So in this case, we're going to use 6,000. You know, I know it's actually 5,800, but all right, divided by 3,000, right? Because they gave us the temperature of that red giant, and then we square that, and this all is a number times the radius of the sun, right? So in other words, we're going to get the radius of the red giant compared to the radius of the sun, and so when you do this. You make sure you do what's in the fraction, the 6,000 divided by 3. Well, you know, I mean, that's not that hard. You square that, and then you multiply by the square root of 10,000. You get approximately, the radius of this red giant is 374 approximately times the radius of our sun. All right, well, we actually know the radius of our sun. You can look that up. You can just Google it. In kilometers, I think it's probably the best. So it's going to be 374 times 696,340 kilometers. Right, that's the actual radius of our sun. All right, so so that'll give us the reason I'm doing it this way is we have to look at, you know, how big this is compared to you know, the size of the solar system, basically, because it asks you in the second part, you know, how many planets will this red giant engulf. All right, so since this thing is 374 times the size of our sun, that becomes, let's take a look, that is approximately 260.3 million, of course, means times 10 to the 6th, kilometers. All right, and the reason I wrote it like that is because just to remind you that, you know, our sun, the distance here. Let me get some more room here. The distance between the Earth and the sun, the average distance between the Earth and the sun, is 1 astronomical unit, right? So 1 AU. We actually know that value, of course. It is 1.5 times 10 to the 11th. I'm sorry, 1.5 times, it's times 10 to the 11th meters, but we're doing this in kilometers, so it's times 10 to the 8th kilometers. All right, so that's the distance between the Earth and the sun. So this thing that is, remember the radius of the red giant, we just calculated this, right? The radius of the red giant is, you know, 260, or sorry, another way to write this would be 150 million, which is, you know, times 10 to the 6th, right? That's the same number of kilometers. But see now, this is 260.3 times 10 to the 6, or million times 10 to the 6 kilometers. So this red giant would envelop the Earth. Let's see how far out it goes. Okay, so it turns out that Mars. So Mars is it's about 1.5 astronomical units. So here's the distance that Mars is. So this is it's not the radius of Mars. Let's see. Let me use a different symbol for that. All right. Instead of R. All right. Here, I just should have wrote it somewhere else. Let's just say the distance to Mars, right? The distance to Mars from the sun is 241 million, which is of course times 10 to the 6th kilometers. All right. And so that this number, the size of the red giant, is just barely larger than that. Well, not barely, but it's it's larger by 20 million kilometers, right? Now that's not going to get us out to the distance of Jupiter, certainly. So the answer to the second part, right? This is the first part. This thing right here, the radius of the red giant is 260.3 times million kilometers, and so the fact that extends out beyond the orbit of Mars means that this red giant would encompass 4 planets. That's an E. All right. Okay. So that's there's our first problem. All right, let's see. Our next one was number 3. Okay, again, we're going to use this formula. Let's see, do that, and let's see. Let me switch to this. All right. Hopefully, you guys can still see that. All right. So number 3. What would the luminosity of the sun? What would be the luminosity of the sun if its surface temperature were 3,000 Kelvin and its radius were 1 AU and then 5 AU? So they're saying 5 billion years from now, when the sun becomes a red giant, what would its all right? So what it's saying is what would be the luminosity at 1 astronomical, when its size is 1 astronomical unit, its radius, I should say, and then part B, what would it be if its radius were 5 astronomical units? So, basically out beyond, that's actually just about to the orbit of Jupiter, just to let you know. All right, so let's do this problem. All right, here we go. So this is number 3. All right, so let's see. How much time do I have left? I'll just set this up. All right, so the luminosity of the star divided by the luminosity of the sun, the current luminosity of the sun, is equal to the radius of the star divided by the radius of the sun, and we square that. And the temperature of the star divided by the temperature of the sun, that's an S, the sun, and we raise that to the 4th power. All right, so that's, of course, the equation that we're going to use. We have to look up, of course, what's the radius of the sun in terms of astronomical units. That probably would be better to turn it into astronomical units. And so the radius of the sun is equal to, I'll have to continue this on the next video. Anyhow, it's going to be 696,340 kilometers, and we know that in 1 astronomical unit.